want. But the latest I'll take it is the Monday after finals. What's the latest I'll take it? All right. Any other questions? If you have a draft you want to show me, yeah, go bring it in. I'll take a look at it. We're going to continue then with our Chapter 8 session. We looked at the photoelectric effect, right? And then we looked at bond breaking using light, the carbon-carbon bond. And then we're going to look at one more aspect of light, and that is light is quantized. When people talk about light, they say it's quantized, meaning what? Meaning that they're steps rather than continuous, right? Steps. That means there's forbidden, between the steps is forbidden. On the steps is allowed. And so this is very common. Light is quantized, but it is a little bit confusing, though, because if you think about the colors of the rainbow, red, orange, yellow, green, blue, indigo, violet, this is going in increasing energy, which means decreasing wavelength, increasing frequency. And so this is backwards from what I was writing yesterday. But as we go from red to violet, is that continuous or quantized? That is, when I go from red to violet, do I go in steps? Like first red, and then orange, and then yellow. It goes in steps, or are some colors of the rainbow forbidden? Like when you look at a rainbow, I don't know if you've looked at a rainbow of colors very, very closely, but are there black, like black lines in the rainbow corresponding to forbidden colors of the rainbow? Or is the rainbow a continuous spectrum from red to violet? Oh, okay, it is. There's no gaps here. And so when somebody says light is quantized, what are they talking about? Are they talking about there are discontinuous range of colors? Or what exactly does that mean, light is quantized? Maybe it isn't, because this looks like it's continuous to me. That is all colors and all energies. This is from low energy to high energy. All energies of light are a threshold for going from one to the next. So, for example, a threshold from going from red to orange, there would be a gap here, like a stair step where all of a sudden you have to jump up to orange. Or does the color vary? We stay at one shade of red and then all of a sudden pop up to one shade of orange. Or do we have a continuous variation of shades of red into shades of orange? What do you think it is? Well, looking at the rainbow, it looks like it pretty much goes continuous. You get a dark red here, and the red lightens up to an orange color. And that happens continuous. So it doesn't seem like there's some kind of threshold or some kind of jump up or gap up in the colors of the rainbow. In fact, the colors of the rainbow are continuous. There are no gaps. And so if the colors of the rainbow are continuous, then what are they talking about quantized for? Is light really quantized, or is light really continuous? The true or false, light is quantized. True. Well, this doesn't look quantized to me. This looks continuous to me. Light is continuous, right? Although that's what it looks like to my eyes. Maybe that's why I need, next time I see a rainbow, I need to get a magnifying glass to look, are there really gaps in the colors? And if I had a magnifying glass, you know what I have to see? I'd see no gaps. And then I think, well, maybe not a magnifying glass, but maybe a microscope. So get a microscope and look, you know, to find its details. And you know what I'd see? Continuous. And then I'd get an even more powerful microscope and then see. And you know what? Continuous, continuous, continuous. I don't see any gaps in the rainbow. The rainbow is continuous. And therefore, you know, I would argue with you, light is not quantized, light is continuous. Energy is continuous. Energy is not quantized. Why can't I have any energy I want? You know, if I go a little higher than violet, is it possible? Yeah, you know what it'd be called? Ultraviolet. Are there gaps in ultraviolet radiation? I'm not allowed this ultraviolet, but I'm allowed this ultraviolet. No. And in fact, if you think about the electromagnetic spectrum, we go from the low energy radio and TV waves all the way to gamma radiation, but there were no gaps. And therefore, energy is not quantized, light is not quantized, it is continuous. True? Or false? You think it's false? Because energy is quantized? Light is quantized?
What's a photon?
A photon is a packet of light.
But it's quantized.
It's quantized, right?
But the light part is just what's emitted when the energy level changes, right?
It doesn't, yeah, that's one way of thinking about it. So it is, a photon means that light is quantized, right? But when I look at this, light looks to be continuous to me, not quantized. And so somebody explain it to me. How can light be quantized when I see that it's continuous? Yeah, right. And so you're right. It's photons. Photons show that light is quantized. So the answer to that question is true. Light is continuous. That's true. You can go from low energy light all the way continuously to high energy light. But it's also true that light is quantized. And so it's at two different levels you have to look at it. Because it's quantized in this sense, you know. When we think about the photon of red, does it have as much energy as a photon of violet? No, a photon of violet packs more punch, is more energetic. And so what do you want? Do you want like a little dense, like this would be like a little BB or something, or a lead shot, and this would be like a big fluffy ball, let's say. Right? And so the photon of red is less energetic than the photon of violet. Right? These are both moving at the same speed, so if this hits you, it would hurt. This one wouldn't hurt as much, let's say. Actually, you can't feel them because they don't hurt. What we say that light is continuous because the range of photons varies continuously. And so if I imagine the photon as a ball, then I could have any size ball I want from here to here. Does that make sense? And I can have even bigger balls, IR, or even smaller balls, UV, right? But any ball I want is available, and there's a whole continuum of sizes. I mean, a whole continuum of energies. But where it becomes quantized is this. Let's say I pick this one. This is the 760 nanometer ball, right? And then I look at the energy of that ball. The energy of that ball is equal to h nu. All right, now if I stick with a 760 nanometer ball, what's the next energy that's possible? So for example, could I have 2 of these balls worth of energy? Yeah, I could have 2 of the balls. If I just get 2 of the balls, then E is equal to 2 H nu. So I have 2 of these. Double the energy, right? But could I have 1.5 of these? No, I can't have half a photon here. And it turns out that the energies of red light at 760 nanometers is quantized. I could have 1, I could have 2, I could have 3, but nothing in between. And so what we say is that E is equal to M times H nu, where N is equal to 1, 2, ... an integer value. And so these would be allowed, but what would be forbidden would be, let's say, 1.5. Another way of thinking about this is this would be like money. Let's say you only had dollar bills. If you only had dollar bills, could you buy something? Well, let's say if you only had dollar bills and you needed a $1.50, is that a denomination that's possible? No. Basically, you have $1, $2, $3. That's it. You can't have a $1.50 or $1 or any of those, right? But is a $1.50 possible? Yeah, $1.50 is possible if you use quarters instead, or something. And so you could do that. You could get that. That energy is not forbidden. The energy itself is not forbidden. It's just forbidden if you try to get that energy using these photons. Then it's forbidden.
You trying to split.
You can't split a photon.
What do you mean by trying to get?
Well, okay, let's say this is $1 here. This is $2, and $3 is the next one. And so if I only had dollar bills, is a $1.50 allowed or forbidden? So $1.50 is forbidden because I only have dollar bills. Right? But it's only forbidden for if I only have $1 bills. Is $1.50 forbidden for everything? No, I could get a $1.50 from something else. That energy is allowed, it's just forbidden in this, with this photon. And so we have a continuum of energies that are allowed. Any energy is allowed, right? Any energy is allowed, but then energy is quantized. Light is quantized. It's quantized when we look at the photons. Does that make sense? And so the energy increments of the violet photon would be, I could have 1 violet photon, 2 violet photons, 3 violet photons, and whatever that energy totals, but I can't have anything between. So basically, if I wanted some energy between, I'd have to pick a different photon, get that. That would be the energy between. And so we have a continuum, and then we have this, quantized, in this sense. And so this is how light is both continuous and quantized. There's no color of light that's forbidden. It's continuous. But there are certain energies for certain colors of light that are forbidden. Therefore, it's quantized. Is that clear? or not? Not? Uh-huh.
Okay, so is it like the idea that a wavelength is continuous, so the light colors are continuous, but the energy of light, which would be considered a photon, is not continuous, so therefore that's quantized? Is that a way of thinking about it?
All right, let me go back to the first part. The first part you said that the wave is continuous?
The light colors, like light colors.
The light colors are continuous? Yeah. And so here you have red, and then violet, and then you could have any wavelength, any frequency, any energy between the two. That's continuous. And so if you wanted a little bit more energetic red, is that possible?
No.
Yes, it's possible. You just get a little bit more. Let's say I have a 760 nanometer photon, looks like this. Let's say I wanted a 760.1 nanometer photon. Possible? 760.1, I'm sorry, takes it to infrared. Let's say I want 759.9 nanometers. Allowed or forbidden?
Forbidden.
Allowed. Let's say I want 759.8. Allowed or forbidden? Let's say I want 759.813678 nanometers. Allowed or forbidden? Allowed. Any number is allowed. Right? It's just a different size photon. That's it. And so in that sense, we have a continuum. Any size photon, we have all sizes from very, very energetic, like gamma ray, to very, very weak, like radio waves. And so you can have any size photon you want. And so there's a continuum of photon sizes available.
So the nanometer, 760.
Yes.
That when we first mentioned that was the size of the wavelength.
Yes.
What's the connection between the wavelength and the size of the photon?
Nothing.
So that's not the size of the photon. That has nothing to do with it.
Yeah. This size that I'm writing just represents the punch of the energy. You know, when I did this, when I was writing that, it's not the size of the photon. This is just to help visualize. You know, if you're going to be hit, you want to be hit with a soft, fluffy ball, or a dense lead pellet. They're both moving at the speed of light. You want to be hit with a soft, fluffy ball. And so this is what I'm trying to visualize in terms of energy. The packet itself, you know, what is the size? What is the size of a photon? It's zero size. What is the size of an electron? It's zero size. You know, and then it picks up. The actual size of it is weird because it has no size. You know,
You just can't have half.
according to particle physics. You know, and a photon travels through space, but it doesn't pick up mass. An electron travels through space, and it ends up picking up mass from the Higgs particles. Have you heard of that? It's pretty interesting stuff if you're into that. But the collider, the Hadron Collider.
It's on Netflix.
Yeah, there's some movies about it on Netflix. It's pretty, and this is all current, recent stuff, so it's pretty good. And so it's kind of weird, but you know, so it's just this energy. This energy. Maybe I should have it backward. I have it backwards because this has a lot of energy. This has a little bit of energy, and so you know I could invert this and say, okay, this is a big photon because it has a lot of energy. This is a small photon because it doesn't have much energy. But the point is that are there certain sizes, like this energy here, is that forbidden or allowed?
It's allowed.
Yeah. This one? Allowed. In fact, there's no forbidden energies between here and there. In fact, in the whole electromagnetic spectrum, there are no forbidden energies. And so when somebody says light or energy is quantized, what they're talking about is if you pick this photon here, and so let's say I'm at yellow light, you know, then the yellow light comes in packets. And we have to have an integer number, so 1 packet, 2 packet, 3 packets, but nothing in between. And so in this sense, it's quantized. In this sense, it's continuous. Does that make sense? All right. So those are some properties of light, and we have to be aware of this. So it's like if you have an electron traveling through free space. Let's say it's just traveling through a vacuum, and so the electron is moving from point A to point B. Is it possible for that electron to move at pretty much any speed? You just accelerate it using whatever, you know, electric fields or magnetic fields. You can accelerate it. Or are there certain speeds for the electron moving from point A to point B that are forbidden?
There's certain speeds.
That are forbidden?
Light.
No, speeds for the electron. I could use a light photon transfer energy to the electron. You know, that's possible. But regardless of how the electron, you know, you think about pushing. If you think about pushing a cart across a parking lot, are there certain speeds forbidden? You know, can you go slow and can you go a little faster?
Yeah.
Yeah. Okay, this is the same thing. Imagine something pushing the electron along or pulling the electron along. You know, electric fields can do that. If I have a positive plate over here and the electron's negative, the electron's going to be attracted to the positive plate. And the more positive I make this plate, that is, the stronger the electric field, the faster the electron will go because it's going to be pulled with more force. And so I can adjust the strength of the electric field by just turning a knob. And so as I turn this knob up, are there speeds that are forbidden for the electron? That is, I know I can continuously adjust the amount of positive charge on the plate by turning a knob. And there's no forbidden ones there. Just turn it up, crank it up. And then this electron starts to accelerate. Now, are there forbidden energies for the electron, or are all the electron energies allowed? All the energies are allowed. And so this is like in the sun. In the sun, electron is in lots of free space. There are a bunch of free electrons, and electrons can vibrate or oscillate at any frequency they want or at any energy they want, right? And so the sun, are there, you know, when the sun emits light from these excited electrons, you know, the electrons don't stay excited forever. Eventually what happens to the electron? They come back down and emit light. And so when you look at the solar spectrum, were there gaps that you saw? You know, distinct gaps of forbidden energies? No, in fact, there are no forbidden energies. So the electron in the sun can have any energy it wants. It has a continuum of energies available. And so it emits the whole rainbow of colors. When you looked at a tungsten lamp, you know, the tungsten incandescent filament lamp, were there any forbidden light colors? No, it was continuous. You saw the whole rainbow of colors because there were no valleys, or, you know, it was just one big band, continuous band of colors. And so an electron in tungsten can get excited. For example, here, you get excited to red, you know, and then it's not going to stay there forever. It drops down and then emits red photons like this. You can excite it a little bit more, right? And more all the way to violet. But there were no gaps here. And so the electron energy in the tungsten filament was continuous. right? Because there were no gaps here. It emitted all the colors of the rainbow. All the colors of the rainbow. But we know that light is quantized in this sense because if you look at that tungsten lamp, the yellow that comes out there is going to be quantized in photons of this size, right? And these photons can be used to do something. The violet photons can pack a little bit more punch right here. The red don't do as much damage. And so that electron, or those, it's not just one electron, those electrons in tungsten filament are emitting all sizes. And I'm talking about not size, physical size, but size in terms of energy. All sizes of photons. All right, so let's go back to our scientific method. You know, there's observation, and then what? Yeah, pattern, say, and then some law, and hypothesis, theory. So the observation of unusual light patterns, what is unusual? Well, one of the things that might have been unusual is this whole idea of quantization, because if you had, let's say, 100 joules of blue light knocked electrons off, then surely 100 joules of red light should knock the electron off. True or false? False. It's false because we know that light is quantized in terms of photons, and the photon energies are different between red photons and blue photons. That's it. But it wasn't just that. The unusual pattern was this. The unusual pattern was for the hydrogen lamp. You know, what does a hydrogen atom consist of? A hydrogen atom consists of one proton and one electron. Now, the electron is here. Obviously, it's going to be attracted to the proton, so it's not going to veer very far away, right? And so it is attracted. But along comes a wave. And this electron, the proton's more like an anchor, but the electron is kind of loose, right? It's light. So a wave comes along like this, and then the electron starts to oscillate with the wave, right? And so a red wave comes along, the electron oscillates with that. And then an orange wave comes, right? And then a violet wave comes, right? And so these waves come, and the waves are just what? Positive, negative, positive. There's these fluctuating electric fields. So the electron's going to go positive, negative, positive, negative, positive. It's going to just oscillate with waves. And just whatever waves come along, the electron should oscillate with, right? And so an electron in a hydrogen atom should be able to oscillate with all the waves, red to violet, and therefore it should be able to, let's say it's oscillating with the violet, it's not going to stay there forever, it drops down and starts to emit violet light. And so an electron in a hydrogen atom should emit the full rainbow of colors. It should emit a continuous spectrum, right? But it doesn't. It doesn't emit a continuous spectrum because when you look at the spectrum, and I forgot to write it down. When you look at the spectrum for hydrogen, you saw red, a green, blue, a blue, and a violet. Actually, let me grab something here. I just need the numbers.
This is a crack. It's like, I'm doing that.
Yeah, something. I like the way it's not weird. You know how to read, right?
I can't take that.
Yes, to answer or
Yeah, that's awkward.
So what it comes down to is this. The red is at 656.3 nanometer. The green is at 486.1. So 486.1, this is green-blue nanometers. Blue is 434.0. It's getting closer to violet. The violet for sure is 410.1. And the intensity, the most intense turns out to be the red. And so the intensity is plotted on the left. This is what we call an emission spectrum. Emission spectrum. Because what we're doing is we're exciting the electron using an electric current. And so it excites the electrons, and the electrons don't stay excited forever. Eventually they'll drop back down. But this is the hydrogen lamp spectrum. And so if the electron is just a little boat in a sea of waves, why can't it just rock with all the waves that come along? In other words, let's say a red wave comes, has a wavelength of 656.3. Let's just change the wavelength a little bit. I'm going to change it to 656.2. If I go to 656.2, well, the electron's happily rocking along at 656.3. A wave comes out 656.2, slightly shorter, just slightly shorter, with a slightly higher frequency. Not even, I mean, very minor, right? Very minor change, but it stops. It won't move. And so what is preventing, is there something, you know, if this is a little boat, all of a sudden it stops and it won't move, well, what's preventing it from moving? Because it turns out 656.2 is forbidden. It's forbidden. Okay, if 656.2 is for, oops, on this side, is forbidden, then let's try 656.4 on this side. Forbidden. No, I drew it backwards from what I have over here. In this case, I'm going increasing wavelength, decreasing energy. So, this is increasing lambda. This way. And so something must be stopping the boat from moving. What is it? You know, maybe did something come and lock the electron in place so now a wave comes along, it can't oscillate? No, there's nothing to lock it in place. They, how do the waves cancel each other? The wave just comes along. Here's 656.3, here's 656.2. You can barely tell the difference. It's only 0.1. 0.1 nanometers is 0.1 times 10 to the minus 9 meters wavelength difference. You can barely tell the difference. 0.1 nanometers, I can't even draw the difference. It looks exactly the same. Unless you kind of blow it up. I blew it up here, so now we can tell the difference. But why does this one not cancel and this one cancel? Because I'm only shooting one wave at a time. I shoot this wave, electron oscillates. I shoot this wave, which is just a hair different. It does not move. Why? And in fact, it doesn't move for a lot of waves. Most of the waves that you pass by here are forbidden. They're forbidden, 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 and forbidden. And so this is a different type of quantization. This is what we say the electron energy in a hydrogen atom, the electron energy in an H atom is quantized. Now this means a different thing than what we just said. You know, light is quantized, energy is quantized. What does this mean?
There's gaps.
That there's gaps. There's gaps. That is, there are forbidden energies and allowed energies. But these gaps, are there energies that really exist? Does a photon with this energy exist?
Yeah.
Sure. In fact, the whole continuum of photons, but for some reason, this electron will not interact with waves of that energy. So this is a very unusual, I mean, there are a couple of, like I said, unusual things. One was the photoelectric effect, depending on the size of the photon here, but the other is these gaps. Why are there gaps here? Why can't this electron oscillate at any frequency, any wavelength, any energy it wants? Well, we don't really think of the why just yet because what's the next step of the scientific method? Yeah, well, there's our pattern here. This is our pattern, and then comes a law. You know, most laws, what they are? Mathematical equations that fit the pattern. And so you look at it, is there a mathematical pattern here? It's hard to see, but it turns out there is a mathematical pattern to the lines. And so the law, we'll call it the Rydberg law or equation. We call it the Rydberg equation, but you could call it the Rydberg law. The Rydberg law is just a mathematical equation that fits the pattern. The mathematical equation that fits the pattern is that the energy of the photon, the energy that this electron will interact with, in other words, the photon energies it interacts with, is equal to a constant times 1 over n, I'm going to call it sub f squared minus 1 over n I squared, where n I and nf are two different numbers. N is equal to 1, 2, 3, ... And so this is the mathematical equation that fits that pattern. You could use this to predict the energies. Where do we get the constant? The constant is just some adjustable parameter. So we adjust the constant so that the answers from that equation match perfectly. And so this is an empirical constant. You get it from the data in the graph. It's like, where do you get the slope from? You get the slope from the graph. You figure out the slope. Well, the same thing. Where do we get the slope from, or the constant? You figure it out from the graph. And figuring out from the graph, the experimental data, and you're going to rename it after Rydberg. We're going to call it R sub h. We're going to give it a negative sign to change the sign so this makes more sense. And so it's going to be n final squared minus 1 over n initial squared. I'm using final initial, but we don't know. It's this n, the two n's are different.
This is only for the experiment, or is it
Okay, is this law good for all the patterns you saw, like the helium, the sodium?
No.
What do you think? No. This law is only good for hydrogen. Right. But that's okay because we can use this law to make some predictions. And the predictions we can use, make, are this. Are there any other lines in here? Perhaps lines we can't see. For example, beyond violet is ultraviolet, and beyond red is infrared. And so we need a special detector to detect these. Actually, we have it. We could only go 380 into the violet. And in the IR, we could only go 900. But there are spectrometers that detect the lines way deep into violet and also deep into the infrared. And so we have a law here. This will be like the comparable to ideal gas law. Do we have to understand the theory that underlies the ideal gas law? Do we have to be able to derive the ideal gas law based on theory? For example, kinetic molecular theory? Pachucci does it in the book, but I skipped it entirely because do we have to do that? No. To use it, it's easy to use. And the same thing with this. I don't care what the theory underlying this is. It's easy to use, and it fits the data. And so something like this, we could do this. We could predict the lines in the UV and infrared, and it's successful. It predicts it, and then you can go out and measure them. And so it works quite well. Works. And then we can use this equation to figure out what n is for those. Like, let's take the 656 example calculation. Let's go lambda equals 656.3. Actually, we need R sub h. R sub h is 2.179 times 10 to the minus. You don't have to memorize this. Times 10 to the minus 19, I think. Let's just take a quick peek. Ten to the minus 18. 2.179 times 10 to the minus 18 joules. That's R sub h. Okay, so we can calculate, we want to know what NF is and what NI is. So we go through and we'll go ahead and do the calculation here. The energy of the photon is equal to, well actually we know what the energy is equal to. The energy is equal to hc over lambda, which is going to equal 1 over, actually I should do this, minus R sub h, minus R sub h, 1 over n final squared minus 1 over n initial squared. But there's a problem with solving this. What is that? We have two unknowns and we only have one equation. And so are we going to be able to solve for n? The answer you think is no, but we do have one restriction. It's not a full equation. N is restricted to being an integer. Otherwise, if n is not an integer, it takes you into the forbidden range, and those aren't allowed. So n has to be an integer. And so what you can do is you can start doing the method of successive approximations. And so you just take a guess and check. Well, you go guessing and checking, that's going to take a long time because n can vary from 1 to infinity. And so how many guesses do you think it was going to take? A lot. But what you'll see is rapidly you can converge on an answer because, when n is kind of small, like for example, let's do 1/2 n finals 2 squared minus 1. And so let's say n initials 1, n finals 2. So we're going from 1 to 2. So this is 1/4 minus 1, which is minus 3/4. But when we start getting to big numbers, let's go n equals 99 minus 99 squared minus 98 squared. Is that a big change? No, it's a tiny change. And therefore, we can converge quite quickly because either the sign is going to be messed up or, the sign should be negative because we're releasing energy. This is emission spectrum. So we're losing photons. And the magnitude is going to be too high or too low, and so we can do it in a limited number of guesses. And it turns out that for the 656.3 line, it works out to this. N final is 2, and initial is 3. And we can do that for each of these lines. So when we do that for each of these lines, we'll get this. We're going from n equals 3 to n equals 2. This one is n4 to n2. The next one is n5 to n2. The last one here is n6 to n2. What about n7 to n2? N7 to n2 is out in the UV. What about n2 to n1? n2 to n1 turns out to be in the UV. And if we go to let's go to n4 to n3 turns out to be in the IR. And so we'll see that, for these lines, there's only a unique set of numbers here that will match. And in this way, we just adjust it. We can go from n3 all the way to n infinity and figure out all the lines. And then we'll change it. We go to n equals 1, figure out all the lines, and then keep going. And doing all the possible combinations, there are only 4 that are visible. The rest are invisible. They're there, but they're invisible. Right? So, potentially there. It depends on how much you can excite the electron in the hydrogen atom. The red is the most intense because, you know why the red is most intense? Well, actually, I shouldn't say. This is all part of a hypothesis, because the law, do we really need to understand what's going on to use it? No, it's just a mathematical equation. All you need is some algebra. No, just a number. Yeah. N is a number. What does N stand for? It's called a quantum number, and it's just a number, and it just is a pattern that works. And so what you're asking is the next step. The next step is to figure out what does N stand for, right? But to use the Rydberg law, do we need to know what N stands for? No. We just need to know what's allowed and what's forbidden. And so what's allowed, N equals an integer from 1 to infinity. What's forbidden? All the other numbers. That's it. And so what we want to do is we want to figure out what does N stand for. And I put in some more detail here, like final, initial, but that's too much detail, because for this we just need to know that it's a number. It's a number, and this number pattern fits this spectrum, this spectral pattern. That's all. And so what can we do with that equation? We can predict other lines. I can predict any line in that spectrum. For example, I could predict that there should be a line at, we can figure it out, n equals 7 to n equals 2, and then figure out where that is. it turns out, well, this is going to be in the UV. It's going to give me a certain wavelength that's down here. And the calculation's easy. The calculation is so easy. It's just the photon, the energy of the photon is equal to minus r sub h, 1 over 7 squared minus 1 over 2 squared. And so 1/49 minus 1/4. And then figure out the energy of the photon. Actually, do you want to do it? Yeah or no? Okay, we could do this. Let's do this. I'm ahead.
I have a question.
Go ahead. So, you know, this one, the invert key helps a lot. So if I do 49 invert minus 4 invert equals, and then I could get that in the parentheses, times 2.17, oops, 2.179. These buttons are so small. 2.179 times 10 to the minus 18 equals this. And so the energy of the photon comes out to 5.002 times 10 to the minus 19 joules. This is going to equal hc over lambda, which equals h nu. We're interested in wavelength, so let's go ahead and calculate. Lambda is equal to hc over the energy. And so I'm going to invert this again and then times it by h. H again is 6.626. Did I talk about h? Yeah? No? 6.626 times 10 to the minus 34 times c. C we'll use to 3 sig figs, but I'm not going to punch them in. It's 3.00. I'm just going to type in 3 times 10 to the 8. A lambda is 397 times 10 to the 368 times 10 to the minus 8 meters. You know what a joule is? A joule is equal to a kilogram meter squared per second squared. And so I have this, well actually I don't need that. H is in joules times seconds, C is in meters per second, so seconds cancel. E is in joules, so joules cancel, and that leaves us with meters. So 3.97 times 10 to the minus 8 meters, which is 39.7 times 10 to the minus 9 meters, which is 39.7 nanometers. Where's 39.7 nanometers? Where's 39.7 nanometers? All the way at the bottom? What's at the bottom? It's not all the way at the bottom. It's UV, right? You should be able to tell me without having to look it up, because you should know UV starts where? Where does UV start?
Nanometers.
In nanometers. Where does UV start in nanometers? Where does violet end? Violet ends at 390, therefore UV starts below 390, so it goes 390 and smaller. So this is going to be UV. So can we calculate? Well, we can. We know that there should be a line here in the UV, and we can measure it. Okay, now that's no problem. This equation works well, just like the ideal gas law. The ideal gas law works well for most gases, but not all. You know, that equation had to be modified. You know, the ideal gas law had to be modified to compensate for intermolecular forces and volume, and we got the van der Waals equation, right? This equation we don't have to modify. You know, this equation works great. The only problem is this equation only works for hydrogen, so maybe we could modify this equation, tweak it a little bit to make it work for helium, the next most complicated atom. But no, they were never able to tweak this equation here to make it work for helium. In fact, it was impossible. No matter what they did to try to adjust this equation to make it work for helium, it just didn't work. It's not something simple like putting on some fudge factors and some adjustable parameters. But that's okay. At least it works for hydrogen. So let's try to figure out some kind of hypothesis. Where does this equation originate from? What is the fundamental description of the hydrogen atom that leads us to this equation? And so the hypothesis was that
There's 2 electrons.
I'm sorry?
Because there's 2 electrons.
It has, well, hydrogen. We're going to just stick with hydrogen atom. Helium has 2 electrons, which makes it more complicated. But at least this Rydberg law works well for hydrogen. It's a fact, and so we should be able to at least, for right now, let's forget about helium, because helium is more complicated. Let's just focus on the Rydberg. Rydberg is experimental fact, right? And whatever theory we come up with we have to be able to spit out the Rydberg law from whatever theory we generate, right? Because Rydberg law is fact, at least for hydrogen. And so what is the hypothesis? Well, the hypothesis is this. And so the hypothesis was that electrons, these ends, you know what the ends correspond to? The ends correspond to, well, let me add some more to the map. The energy of the photon can be thought of as some kind of change in energy, right? Delta E. Excited electron drops back down, so there's a change in energy and it spits out a photon. And so this energy of the photon can be thought of delta E, which is E final minus E initial. So the Rydberg equation kind of has this in there. That is, when we look at the Rydberg equation, it's minus R sub H 1 over N. This is why I call it final, minus 1 over N initial squared. And so when I'm thinking about the energies, the final energy is minus R sub H over N final squared, minus R sub H over N initial squared. And so this is what we have. This is the final energy. In other words, the energy, and we're going to call these allowed energies. Allowed energy for the electron is equal to minus R sub H over N squared. Those are the allowed energies. And so the hypothesis is this. The allowed energies correspond to orbits. And the theory that this led to, this whole idea of orbits, was named Bohr theory. Okay, for the Bohr theory, the lowest possible energy for the electron is this. The lowest possible energy is if n equals
1.
1. If n equals 1, then I'll have the first orbit here. So I've got an electron here, it orbits around it, and we call this E1, lowest possible energy. The next energy would be a higher energy orbit, E2, and then E3, and then dot, dot, dot. I'd have to go a very long distance, but the highest possible energy is E infinity. E infinity. So electrons out here, the highest possible orbit. the highest possible orbit, what is the, let's calculate the energy for E infinity using the empirical equation that we have. And so the energy is, yes, the energy is 0. E infinity is equal to minus r sub h over n squared. And n is infinity, so we're just going to minus r sub h over infinity squared, which is, yeah, to be 0. And so here, E infinity is 0 joules. This is the highest energy we have. This is backwards from the way we normally think. The way we normally think is that the lowest energy should be 0, and any energies above that should be higher. And so this is weird because now what we're going to do is we're going to place the highest energy possible as 0. And any energy lower than that will be negative and lower. And so the lowest possible energy is, it's an easy calculation. What is the lowest possible energy for the electron? Minus 2.179 times 10 to the minus 18 joules. That is the lowest possible energy. Can we go lower than this? No. The highest possible energy is 0. And so we're going to have a range of energies like this, from minus 2.179 times 10 to the minus 18 joules. How much water can you heat up with minus 2.179 times 10 to the minus 18 joules? If I had a mole of water, 18 grams, and I put in 2.179 times 10 to the minus 18 joules in there, am I going to heat up much water? No. I'm not going to heat up much water. But you know what? If I put that 2.179 times 10 to the minus 18 joules into this electron, so I put all that energy into this electron, do you know what's going to happen? Well, electrons conserve. And so from the surroundings comes 2.179 times 10 to the minus 18 joules. This electron absorbs 2.179 times 10 to the minus 18 joules and gets bumped up to, well, minus 2.179 plus 2.179 gives me 0. And so what this corresponds to is this. 2.179 times 10 to the minus 18 joules won't do anything to a mole of water, but it will knock an electron, a hydrogen atom, from the lowest energy level to the absolute highest energy level. In other words, we call that process ionization. So this tiny bit of energy is all that's required to ionize a hydrogen atom. It's ionizing a hydrogen atom because when we do this, something else came from this Bohr theory. What else came from the Bohr theory is using some physics, Bohr predicted the radii of these orbits. And so the radii is like this. Let me get the right number here for the radii of the Bohr orbit. A naught, 0.53. The radius of the Bohr orbit comes out to n squared times a naught, like this. And a naught is a constant. It's 53 picometers. And so the first orbit is 1 squared times 53 picometers, which is just 53 picometers. So R1 is 53 picometers. R2 is going to be 2 squared times 53 picometers. In other words, 4 times a naught. R3 is 9 times a naught. R infinity is infinity squared times a naught. Where's that electron? The electron is infinitely far from the nucleus, meaning that electron's gone, long gone. This is what we call an ionized electron. Ionizing is knocking the electron. The electron's never coming back. It could, but at this point, it's long gone. All right, so what we do is what happens in the what we call the hydrogen lamp, which is an electric discharge lamp. And so in the hydrogen lamp, there's an electric discharge. Electric discharge is like a lightning bolt, but it doesn't look like a lightning bolt. But it's kind of like a lightning bolt. The lightning bolt goes through, and it excites the electrons in the hydrogen atom. And so what happens is an electron gets excited from the first to the third level, the third floor. It doesn't stay on the third floor forever. It's got to come back down. And so as the electron drops back down to the second floor, there's an electron going from n equals 3 to n equals 2 will emit what color light? (656.3 nanometer red light). Does that make sense? And so electron gets promoted here. An electron that gets promoted from the n, up here all the way up to the n equals 4 level. And so the n equals 4 electron doesn't stay on the 4th floor. It could go to the 3rd floor. If it goes to the 3rd floor, it emits infrared. If an electron from the 4th floor goes all the way to the 1st floor, it emits UV. But if an electron on the 4th floor goes to the 3rd floor, it emits 4th floor. Oh, I just said that, infrared. An electron on the 4th floor dropping down to the 2nd floor emits, as an n equals 4 to n equals 2 transition, emits blue-green, green-blue, right? What was it, 489 nanometer? Is that right?
46.1.
46.1. 46.1. Can an electron go from the 3rd to the 2.5 floor? No, that's forbidden. So all those colors between here and here are forbidden. We have an energy gap there.
Just like the colors are common.
Well, colors or light wavelengths. I should say all those wavelengths are forbidden. Colors, because in this region it would be visible light, and so these colors would be forbidden here, or close to visible light.
I'm confused if they just said the colors were continuous.
The colors are continuous, yes. There are no forbidden colors. There are forbidden colors for the hydrogen atom. The hydrogen atom should not have forbidden colors, but it does. And so this is the hypothesis, this is the theory. The theory is that hydrogen has forbidden colors because the electron can only occupy these allowed orbits and none other. I'll talk about it more in just a second. Did you have a question, Madonna?
Oh, no, it was, you answered it.
Okay. Now, the situation is, if this is an orbit, why can't it just orbit a little faster? And if it orbits a little faster, it'll just go out a little bit farther. Or why can't it orbit a little slower? If it orbits a little slower, this could be like a slowing orbit, space debris. Eventually, the electron can crash into the nucleus. Right? I mean, what's preventing the electron and the nucleus from coming together?
Propulsion.
They're attracted to each other. They're attracted. There's no wall there, right? And so why can't the electron orbit anywhere it wants? Well, this is the confusing thing. A lot of people think science should be able to answer why, right? But when you start doing a lot of science, you'll realize that sometimes science just doesn't answer why. Sometimes science just is a description. This is a description of nature, right? Why? Who knows why? But this is it, right? This is how nature is behaving, and therefore this is how nature is behaving. That's all. Science isn't. In other words, we take this as a postulate. A postulate is. Did I talk about postulates yesterday? A postulate is just taken without proof. How can I prove? Well, how I can prove it is easy. It just doesn't happen. You saw the spectrum, right? Spectrum says it doesn't happen, therefore it doesn't happen, therefore this must be the description of what's happening, and for some reason these are all forbidden, these are all forbidden, these are all forbidden. The electron cannot be any distance, so it's got to jump from one to the next. In other words, the speed. If I slow this down just a hair, forget it. It's not going to work. Why? Because that's not what's observed in nature. And that's it. All right. So the answer, because one of the questions physicists would ask is, why doesn't the electron spiral into the nucleus, crash into the nucleus? And the answer, it can't. Right? Why doesn't the electron orbit a little closer, a little farther? It can't. You know, that's it. For some reason it can't, because that's the way nature is dictating this thing.
So it's fixed. It doesn't even have to slight adjust it.
No, it can't even slightly adjust. You can't just give it a little bit more of a nudge and have it orbit at 53.1 picometers. Forget it. It's not going to happen. It's going to be at 53 or nothing here, and then 4 times 53 or nothing, and then 9 times 53 or nothing. And so that's fine. We can accept this postulate if this theory, what else should a theory do? A theory should describe what's happening. So this theory is describing what's happening with the electron and the hydrogen. But a theory should also predict. But maybe the good thing about this Bohr theory, so we don't have to think about these, you know, these are lingering questions. You know, that's not a satisfying answer, is that? Or a satisfying description. It just can't. But the Bohr theory could not predict. No matter how much they tweaked the Bohr theory, they could not make it work for helium, let alone anything else. They could make it work for very bizarre species. And so the only tweak that they could do to the Bohr theory was they could predict these species: helium plus, lithium 2 plus, boron 3 plus, beryllium 4 plus. Oh no, I'm sorry, I messed up. Helium plus, lithium 2 plus, beryllium 3 plus, boron 4 plus, etc. But these species are weird, rare, not common, only created in the lab, not found in nature as that. So if you find something in nature, then the Bohr model, the Bohr theory did not work. Therefore, the Bohr theory was abandoned. So that was the end. So this whole idea of orbits is wrong. This radius is wrong, because it turns out, but this is right. This equation is fact here, right? This equation, there's nothing wrong with this equation. And so whatever new theory we generate, it better spit out the Rydberg equation. Otherwise, the new theory will go the route of the Bohr theory. And so the new theory, well, there were some new developments that led to this new theory. And so this is what I call Theory 1. Theory 1, which is quantum, right? Theory 1, Bohr, was knocked out to be replaced by the next theory, Theory 2, which is quantum mechanics. But there are some scientific developments that occurred that led to quantum mechanics. And so let's talk about these. One scientific development is the wave-particle duality. And the second scientific development is the Heisenberg uncertainty principle. Quantized energy carries over, right? I mean, energy is still quantized. We can see that in the hydrogen spectrum. Energy is still quantized. Do you know red food color? Do you expect a rainbow of colors from red food color? No. But we did expect a rainbow of colors from the hydrogen atom. It's different. You know, red food color has the electrons locked in the molecule of red food color. And there we have bonds and a whole bunch of other stuff. So there it makes sense that not every energy is allowed for the electron in a molecule of red food color. But for a hydrogen atom, it is. So this whole idea, energy is still quantized, carries over for the H atom, for helium, for the others. So let's talk about the wave-particle duality first. This is de Broglie. And so wave-particle duality, we know light has wave-particle duality. Light, you know, has this oscillating field, and so it's like a wave, but light is also like a particle because we have these photons of light. It's like this. And so how do you combine it together? When you combine it together, we see something like this, you know, a wave packet. Wave packet, something like that. Well, we don't have to worry about that wave packet. We know the light is going to have characteristics like this and photons because wave packets come in different sizes, we could say, different energies. And the photoelectric effect is very clear. What de Broglie said was that not only light has wave-particle duality, but matter has wave-particle duality. You know, we have a particle of matter. Okay, these particles of light, are they real particles? I mean, do they have mass? No, they're just packets of energy. And so when I say particle of light, you know, it's not the same as a particle of matter. Whereas a particle of matter, yes, definitely, a particle of matter has mass. An example of a particle of matter would be red food color molecule, something like that. Okay, it turns out when particles of matter are moving, do you know they move at certain wavelengths? And so the wavelength that matter moves at, and so this would be lambda matter. Lambda matter is not c over nu. This is just for light. Lambda matter is equal to h over mass times velocity of the matter squared. H over mv squared. Oops, not squared, just h over mv. Sorry. So let's look at an example here. Let's look at an electron. Let's say an electron is moving at a speed of 0.1 times c. Let's see what the wavelength is. If the electron is moving at a speed of 0.1 times c, then lambda for the electron is equal to H over mv. So H is Planck's constant, 6.626 times 10 to the minus 34 joules times seconds. The mass of an electron, we could look up in the back of the book. The mass of an electron is 9.1. Let's just go. 9.1 times 10 to the minus 31 kilograms. I'm only going to go 2 things. 9.1, let's go 9.10 times 10 to the minus 31 kilograms. 9.109. We'll go for it. 9.109 times 10 to the minus 31 kilograms, the mass of one electron. The velocity is 0.1 times the speed of light. And so that's 0.1 times speed of light, 3.00 times 10 to the 8 meters per second. Let's see. This. What is the wavelength of the electron? I'm sorry? Point.
No, 2.42.
2.42 times 10 to the negative 11. So what are the units here? So let's try to figure out the units. Kilogram meters per second. The second here, and then joules is kilogram meter squared per second squared. So that takes care of that. One of these seconds will cancel that. This is kilograms, so kilograms cancels kilograms. Meters per second cancels one of the meters and the last second, and that gives us meters. 2.42 times 10 minus 11 meters is equal to 20. Oh no, what is it equal to? If I want to make this 10 to the minus 10, so I make this smaller, I got to make this bigger, right? And so this would be 24.2 times 10 to the minus 10 meters. You know what 10 to the minus 10 meters is called? It's called an angstrom. And so this is 24.2 angstroms. Okay, why angstroms? Well, this is 24.2 angstroms, which is equivalent to 0.242 picometers. Angstroms and picometers are significant. Why? Oops, I'm out of time. Why are they significant? Because angstroms and picometers are what we use to measure the size of an atom. A hydrogen atom, remember the first Bohr radius? The first Bohr radius is 53 picometers. This is kind of halfway between them. The radius of a hydrogen atom, do you know what the radius of a hydrogen atom is? Half an angstrom, or about 50 picometers. This is the radius, actually 53 picometers. And so we'll talk about this more tomorrow.